Good evening, everybody, or good morning, or good afternoon, depending on your time zone. This is the beginning of everything. In the next half hour, I'm going to try and describe the origin and the very early history of the universe. So, as Mike has already said, this is part of the series of the universe half an hour at a time. This is the first of 4 talks, the others coming up in subsequent weeks. So what am I talking about for the next half hour? I'm talking about the creation of the universe. When did it happen? 13.8 billion years ago. How long did it take? About 3 minutes to make a universe. Where did it happen? Well, it didn't happen at one particular point in space. It happened everywhere. Why did it evolve the way it did to give us the universe that we see today? Well, that's because of the laws of physics. And how do we know all of this? Same answer, because of the laws of physics. So the question is, how do we know what those laws are? How do we know what the rules of the game are that dictate the way the universe should be? If we want to know the rules of the game of, for instance, the game of chess, would a snapshot like this be enough to tell us what the rules of the game are? Well, not really. That's not enough information. If we could watch a video of lots of people playing lots of games, then we could start to understand what the rules are. But with just a snapshot, that's not enough. And the question is, if we only have a snapshot of what the universe is doing at the moment, how can we possibly work out what the rules are in terms of how the universe came into being and how it's evolved to be as it is today? Well, I've got here a snapshot of a galaxy, but what we can do is take a snapshot of more than one galaxy. For instance, in the Hubble Deep Field, we're looking at thousands of galaxies, all at various distances. Some of them are quite close to us, but some of them are many, perhaps billions of light years distant, and hence the light has taken a few billion years to reach us. So we're looking at them as they were billions of years ago. So even a single snapshot like this can actually give us valuable information, effectively going back in time from the present to, well, as deep as this particular individual image can take us, perhaps 10 billion years into the past. So we can get an idea of how the universe is changing because we have this aspect of looking back in time. Not quite as good as a video of the entire evolution of the universe, but it'll have to do. But the universe looks very complicated, it looks very complex. How can we possibly hope to understand the rules of the game that resulted in something that looks like that? Well, bear in mind, just because something is very complex doesn't mean the underlying rules are difficult for us to understand. For instance, we can look at this mathematical collection of pixels. Perhaps some of you recognize it as part of the Mandelbrot set. And we can zoom in and we see more detail, and if we wanted to, we could keep zooming in and the pattern never repeats. And you can say that this is an infinitely complex mathematical pattern. So how complex must the mathematical formula be that gave rise to this very complex pattern? Well, the formula is actually that one. We don't have to worry about what the Z and the C actually mean. The point is, a very simple formula, if applied the right way, can give us what seems to be a very complex, perhaps an infinitely complex result. So just because the universe looks very complex doesn't mean the underlying rules are beyond our comprehension. One of my favourite quotes from Einstein is actually this one: "The most incomprehensible thing about the world is that it is comprehensible." And you can replace world with universe if you wish. In other words, despite the fact that there's no good reason why we should be able to comprehend the rules of the universe, it looks like we can. So what's the flow of thought that starts our understanding of the way the universe is put together? We can observe that galaxies are moving away from each other and away from us. We've known this for the past century or so. And from that, we conclude that the universe is expanding. In other words, certain galaxies are a certain distance apart now, but they used to be much closer together in the past. And we can make observations not just of the universe, we can make observations on Earth, for instance, we can start to understand what matter is made of. We can do experiments. We can do experiments in a particle accelerator, for instance, to try and understand what are the basic constituents of matter. We can do experiments like the Large Hadron Collider, and that helps us understand the nature of matter, and we should be able to link that to the nature of how the rest of the universe is put together. But we do have to make some assumptions. We have to assume that if we're talking about the laws of physics in one place must be the same as the laws of physics in another place. If that were not true, if the laws of physics in England were different than the laws of physics in Australia, we would have no chance of understanding the world or understanding the universe. And similarly, we must assume that the laws of physics now are the same as the laws of physics yesterday and the laws of physics tomorrow. If today we find we let go of an apple and it falls downwards, but tomorrow we do the same thing and it falls sideways, again, we have no chance of understanding how things work. We have to assume that the laws of physics are immutable. So we conclude from all of the above that the universe was created in a hot, dense state 13.8 billion years ago, and ever since then it's been expanding and cooling. But the question we can ask ourselves is, where did everything come from? We look into the universe and we see hundreds of billions of stars within our galaxy, and we see billions, if not trillions, of galaxies within the observable universe. Where did all of that stuff come from? And when we're trying to make sense of this and looking back in time and effectively winding the clock back to, if the universe is like this now, what did it look like billions of years ago? We can ask ourselves the question, how far back in time can we go and still be fairly confident that we understand what was happening? How far back can we go and still believe that the laws of physics still hold? Can we go back to the first year of the 13.8 billion year history of the universe? Yes. Can we go back to the, can we go back to the first day? Yes. Can we go back to the first hour? Yes. Can we go back to the first minute? Yes. The first second? Yes. Can we go back any further? Can we go back to the first millisecond after the point of creation and still believe that we understand what was happening? Yes. Can we go back to the first microsecond, the first millionth of a second? As far as we can tell, yes. What about the first nanosecond? Yes. What about the first picosecond? 1/trillionth of a second after the Big Bang. That's the point at which we have to, with a hand on heart, say we are not absolutely sure we can go back any further than that. Before the first picosecond, before the first 1/trillionth of a second after the point of creation, we don't know what happened. We can hypothesize, but we can't prove anything. Everything after that first picosecond is relatively well understood. Relatively, of course, being a little bit of a caveat there. I'll say why that picosecond watershed has come to be. So, in this particular talk, I've given you a little bit of a rambling introduction, and then I'm going to give you, on the next slide, a few basic ideas which we'll need before we look at the timeline of the birth of the universe. We'll look at the first fraction of a second, the first few seconds, then the first few minutes. Then we'll have to change gear slightly, or we could be here all night. We're going to change gear and look at the next 377,000 years. Then we'll change gear one more time and bring ourselves up to date for the next 13.8 billion years. So what's this idea of what do we need before we can make sense of what's coming? Well, what we need is to understand that we are made of atoms. I would hope that comes as no surprise to most of you. An atom, a positively charged nucleus and negatively charged electrons. Given enough energy, we can take an atom and effectively tear it apart, or at the very least look inside it and see what it's made of. A nucleus and a collection of electrons. An electron is a fundamental particle. In other words, as best we understand it, it's not made of anything else. We can't take an electron, cut it in half, have a look inside and see what it's made of. It appears to be just an electron. whereas the nucleus is made of smaller particles. If we had enough energy, we can take a nucleus and look inside it and find that a nucleus is made of some combination of particles called protons and neutrons. And that's not the end of the story, because those are also made of smaller things. We can take a proton and, given enough energy, we can look inside and we find that they're made of particles called quarks. We don't have to worry about why they're called that. We don't have to worry about what they are. All that we care about is that quarks make up protons, protons make up a nucleus plus electrons make up an atom. We have this idea of a sort of Russian doll type hierarchy in terms of our understanding of how matter is put together. And as I've said, it takes a certain amount of energy to look inside an atom. It takes more energy to look inside a nucleus. It takes more energy to look inside a proton. So there's a sort of implicit energy scale here from low energy to high energy. To a physicist, energy is pretty much the same as temperature. And remember that we've decided that the universe was born in a very hot, dense state and ever since has been expanding and cooling down. Which means if we're going from low energy to high energy on this diagram, that means we're going from cold to hot. But if the universe started hot and is now cooling down, that means time runs upwards in this diagram. In other words, the universe was built from the bottom up. If we start with a load of fundamental particles, eventually, when the universe is cold enough, we can start putting those particles together to make protons. We can't do that immediately because the universe is simply too hot. If we try and put quarks together while the universe is still hot, the proton will have so much energy, it'll just break down into its quarks again. And similarly, we have to wait a little while until the universe has cooled down even further before protons and neutrons can get together to form a nucleus. And similarly, we have to wait even longer before the universe is cold enough that nuclei and electrons can get together to make atoms. In the early universe was simply too hot to make atoms. If nuclei and electrons tried to get together, they would have so much energy they would just rip themselves apart. So there's the idea, Russian doll, and we're moving from the bottom upwards, from fundamental particles building to more and more complex structures. So let's start from t equals 0, the moment of creation. What can we say about t equals 0? What happened at that instant? Well, perhaps it's no surprise to say that science cannot provide a definitive answer to what happened at t equals 0. Maybe somehow we got something from nothing. Maybe there was nothing, and then somehow we managed to get a whole chunk of energy with which we used to make the matter of the universe. If we've got some energy, we can make matter because we know what the exchange rate is between energy and matter. Einstein told us that E equals mc squared. So if we could somehow get some energy, we can make a universe. But how can we just get energy from nothing? How can we get something from nothing? That sounds really weird, and it sounds like a cheat. But actually, we have found that quantum theory, which describes the world on a very small scale, well, quantum theory is weird, and quantum theory does allow you to get something from nothing. So maybe that's how the universe began. But we don't know. A lot of people believe it might be something like this, but there's plenty of alternatives, and the bottom line is we can't prove this. If we move forward in time, let's go a tiny fraction of a second forward. Let's go to this ridiculously short length of time of 10 to the minus 35 seconds after the creation of the universe. The universe has now expanded until it's about the size of a golf ball. By the universe, I'm referring to the observable universe. Who knows what's going on outside of this? In other words, everything that we now see within the observable universe, all the stars, all the galaxies, inside a sphere of radius tens of billions of light years, all of that stuff used to be a lot closer together in a much smaller volume, a volume equivalent to a golf ball. Takes a little bit of imagination to figure out how that could be. And just like a golf ball, the universe is not perfectly smooth, but it has dimples in it. Not dimples in the sense of depressions in the surface, but dimples in the sense of variations in density. It's not perfectly uniform. There are variations in density throughout the universe. Eventually, when the universe is much, 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 much bigger, those variations in density under gravitational collapse will form the density variations that will give rise to galaxies and clusters of galaxies. But we're getting a little bit ahead of ourselves. Let's back off a bit. Let's move forward from that ridiculously short length of time to 1 picosecond, 1 trillionth of a second after the Big Bang. The universe has now expanded from the size of a golf ball to a size comparable to the size of the solar system. Okay, the solar system doesn't yet exist, but this is just to give you an idea of scale. The temperature has now fallen to something of order 10 to the power 15 Kelvin. And the energy of each of the constituents of the universe, we've taken this energy that we get somehow from nothing, we've taken that energy to make a whole load of particles, quarks and electrons, and I'm sure loads of other particles as well, but just for simplicity, let's just call it a soup of quarks. The constituents of the quark soup have a certain amount of energy if the temperature is 10 to the 15 Kelvin, and we can reproduce that amount of energy in the Large Hadron Collider. And that is why we say that from 1 picosecond onwards, we can test our ideas. If we have a hypothesis of what we think was happening from this point onwards, we can test it because we can reproduce those energies in the laboratory. Up to this point we couldn't, from this point onwards we can. That's why I'm saying that from a picosecond onwards, we can test our ideas, and that's where we think the laws of physics are sound. Okay, what are we actually generating? Well, energy and matter are continually exchanging back and forth. I've said the exchange rate, if you like, is given by E equals mc squared. If we have a certain amount of energy, we can create a certain amount of matter. But what actually happens is, if you have a certain amount of energy, you will generate equal amounts of matter and antimatter. What is antimatter? Well, antimatter is a sort of mirror, if you like, of matter. Every particle has an equivalent antiparticle. For instance, we're made of protons and neutrons and electrons, and an electron will have an antiparticle equivalent called an anti-electron or a positron. It's very much like an electron, but instead of having a negative charge, it has a positive charge. And whenever energy makes matter, it makes equal amounts of matter and antimatter. And we can represent that. I don't know how to represent energy, so I'll just put a big capital E on the screen. So energy can make pairs of a particle and an antiparticle. Now, okay, it's probably not going to be a tangerine and an anti-tangerine, but the point is it doesn't actually matter. Energy is making a particle of matter and a particle of antimatter. What happens after they're made? They will annihilate and produce an equal amount of energy. And then that energy can go on to make another particle and antiparticle. Again, it's very unlikely that that will be a hot dog and an anti-hot dog, but it doesn't matter. It doesn't matter if we're talking about quarks, or talking about electrons, or talking about other particles. Energy makes matter, matter makes energy, energy makes matter, back and forth and back and forth and back and forth. But somehow, something happened that we don't quite understand. Somehow, although we would think that matter and antimatter are made in equal amounts, somehow matter gained a small excess over antimatter. And we'll return to that in a little while. But if we imagine what that looks like, for instance, what if we made this many particles of matter and a smaller number of particles of antimatter? We're not saying we understand how that came to be, but it looks like that's what actually happened. And we know that when matter and antimatter come together, they annihilate and produce energy. So you can see in this case, the first few tangerines and their anti-tangerines are going to produce energy, but one of them is going to be left over because there's more matter than antimatter. So what do we end up with? We end up with a universe which appears to be full of energy, and that energy is usually in the form of radiation, light. not necessarily visible light, light in its general sense, plus we have some matter left over because of that asymmetry. So we have a universe full of light and a little bit of matter. But let's be grateful, because that little bit of matter that's left over is all of the stars in all of the galaxies, and the sun and the earth and you and me. So it's just as well that there was an asymmetry between the two, because otherwise I wouldn't be giving this talk and you wouldn't be listening to it. So let's move forward a little bit. Let's move forward to a millisecond. Matter and antimatter are continuing to pop into and out of existence. Matter and antimatter to energy, back to the pairs again. Now at some point, at about a millisecond or so, it is possible for protons and neutrons to start to form. In other words, it's now cold enough for some of these quark particles to start to come together. And when you have a certain combination of three quarks, well, we call that combination a proton. We don't have to worry about why and how. And a different combination of quarks is what we call a neutron. So we can think of a proton and a neutron as simply being a label for this combination of quarks or for that combination of quarks. And because matter is converting to energy, is converting to matter backwards and forwards, protons are changing into neutrons and neutrons are changing into protons, back and forth and back and forth. And this continues on. If we jump to something of order 1 second, the universe has now continued to expand and cool, and the universe is now about 1 billion Kelvin. Although that sounds very hot, it's actually too cold for protons and neutrons to continue swapping back and forth. And as it happens, protons are a little bit lighter than neutrons. How do we know that? Because we can measure that in the laboratory. And as far as we can tell, a proton and a neutron now are just the same as protons and neutrons were billions of years ago. So if protons are a little bit lighter than neutrons, what happens is that the universe makes more protons than neutrons. It turns out to be in the ratio of 75 to 25. Why do we get more protons? Well, there's a fundamental tenet that nature always favours the lowest energy, or the lowest energy state, which in this case also means nature favours the lowest mass. If you want to think of it this way, you can say protons are a little bit lighter than neutrons, so they're easier to make, so the universe makes more of them. The point is that we can predict how many neutrons and protons are made by the Big Bang if we understand the laws of physics 1 second after the Big Bang. If we go forward a few extra seconds now, so we're now at the stage of being something like 2 or 3 minutes after the Big Bang, neutrons are unstable. How do we know neutrons are unstable? Because we can measure them in the laboratory. And again, we assume it's no different. Even though we're talking about 2 minutes after the Big Bang, neutrons behave the same way. Some of those neutrons decay and become protons. So in that representative set of 16 particles, which I showed a moment ago, some of the blue have changed into red. So in other words, instead of having 12 plus 4 blue, we now have 14 red representing the protons and 2 representing the neutrons. At this point, 2 or 3 minutes after the Big Bang, the universe has cooled to a temperature of some 100 million Kelvin. And at this point, nuclei can now form. It's now cold enough that protons can start grabbing hold of neutrons. Up to this point, if a proton had tried to bond with a neutron, they would have had so much energy in the hot universe they would have just broken apart. But now the universe is only 100 million Kelvin, it is possible for neutrons and protons to get together. And what they really want to do, what protons really want to do, is to get together with neutrons in a particular structure. And that structure is indicated here. What they really want to do is 2 protons to get together with 2 neutrons. Why? Because we can measure in the laboratory and confirm that that is a very stable structure. That's what protons and neutrons really want to do. They want to get together and pair up 2 protons and 2 neutrons. We call this combination an alpha particle, or sometimes we might call it the nucleus of a helium atom. But in those representative 16 particles that we've got there, we can see that 2 protons and 2 neutrons can pair up. But we're left with 12 bachelors. Those haven't got any other neutrons to pair up with to make more of these alpha particles. There simply aren't enough neutrons to go around. So what we're left with when all of the neutrons have been soaked up into these alpha particles is a load of free-floating protons, which we can describe as the nucleus of hydrogen atoms if we wish, and the nucleus of helium atoms. And after 3 minutes, the relative abundance of hydrogen and helium is fixed. After 3 minutes, the universe can't change protons into neutrons and change this ratio. The abundance of helium relative to hydrogen is now fixed. And the Big Bang theory predicts that we should have this much. For every 4 kilograms of helium, we should have 12 kilograms of hydrogen. Protons and neutrons are roughly the same mass, so we can simply scale up if we wish. When we look out into the universe and ask, well, how much is actually out there? What do we find if we look at all of the gas in the universe? We find 3/4 of it is hydrogen and 1/4 of it is helium, just as predicted by the Big Bang theory. That is one of the reasons why we believe that the Big Bang theory is the correct theory for describing how the universe came into being, because it gets predictions like that, which we can test with observations, and it gets the predictions right. Let's move rapidly forward 377,000 years. Why? Because nothing very interesting happens for the next 1/3 of a million years or so. The universe continues to expand and the universe cools. Eventually, the universe reaches the temperature of about 3000 Kelvin, which it does at this particular time. Why is 3000 Kelvin important? At this temperature, nuclei can now hang on to negatively charged electrons. Again, before this point, the universe was simply too hot, and there was too much energy floating around such that a nucleus could never hang on to the electrons. They had so much energy they would simply disintegrate. But at this particular temperature, it is possible for a nucleus to hang on to electrons, and so for the first time in the history of the universe, atoms exist. And the universe changes from a plasma, which is just a big cloud of positive and negative charges floating around. The universe changes into a collection of atoms, which are all electrically neutral. At this point, the universe turns transparent. And so at this particular point, light that was trapped in the plasma and bouncing around like a ball in a pinball machine, light then experiences the fact that the universe has turned transparent and the light is released. The light can now fly through the universe without continually getting bounced around by these positive and negative charges. And we see that light, not in quite the same way as would have been seen at the time, when the universe was at a temperature of 3000 Kelvin. What does 3000 Kelvin look like? If you take an object and heat it up to 3000 Kelvin, it looks white hot. It's producing a very large amount of visible light. But that's not what we see, because the visible light that would have been generated at the time, with a wavelength of about a micron or so, the universe is now 1,000 times bigger than it was back in this day, and so the wavelength of the light has been stretched 1,000-fold. So instead of being a micron or so in size, the wavelength is now millimeters in size. And what do we call electromagnetic radiation that has wavelength of millimeters? We call that microwaves. And so that's what we see. The light that was released 1/3 of a million years after the Big Bang, when the universe turned transparent, that's what we see as microwave background. This is an all-sky picture. Microwaves are coming from all directions. It's virtually the same intensity from all directions, but this particular map has been color-coded to show you that some regions are a little bit hotter than others. In other words, there's just a slightly higher intensity from some regions and a slightly lower intensity from other regions. So it's actually very uniform, but this picture is exaggerating those small differences. So it's not perfectly smooth. And these variations that we can see, these red blobs or blue blobs in the previous picture, they are the result of the little dimples that we saw in the cosmic golf ball. These small variations in density when the universe was the size of a golf ball have now mapped themselves or imprinted themselves onto these small variations in microwave intensity that we see in the microwave background. And that's why people are intensely studying the microwave background, because it gives us a probe to that very early universe. And as I said, we can think about these dimples in the golf ball which gave rise to the variations in the microwave background, and we can ask what happens to those dimples if we run forward a long way in time. Well, we can't run a video of the universe, but we can run a simulation and ask if we take a little cube of matter with small variations in density and we allow gravity to take hold in those small variations, what happens? We find the dense parts become denser, and we find that the universe collapses into a structure which we can think of as a web-like structure with lots of filaments and lots of voids, and we see some regions become very dense, and this is precisely the regions where galaxies and clusters of galaxies are going to form. And we'll see next week's talk. So let's fast forward again the next 13.8 billion years to the present day. We've seen that if we accept the Big Bang theory, then we can see how hydrogen comes into existence. It takes 3 minutes to make all the hydrogen that exists in the universe. And if we have enough hydrogen, we can pretty much understand everything else. And we can understand stars and galaxies. Again, more of that in the next talk. But if we start with enough hydrogen, not only can we understand galaxies and stars, we can understand planets, and we can understand trees and mountains and snowflakes and rainbows and cats and... Okay, maybe not cats. I don't think anybody really understands cats. But if we start with a lot of hydrogen, we can pretty much understand how everything else came to be. Yes, I'm skipping over, of course, a lot of the detail of cosmic evolution, but you get the basic idea. And yes, we do still have some gaps in our understanding. The jigsaw is by no means complete. The remaining questions are, why did matter win over antimatter? What caused the asymmetry? We can study the asymmetry, we can do particle physics experiments, and we can see the asymmetry between matter and antimatter, but what caused it in the first place? We can also ask the question, what is dark matter? This rather odd, invisible stuff which appears to be out there, as best we can tell, that seems to be making the galaxies rotate at the wrong speeds. What is that? We don't know. What is the even more enigmatic dark energy? This is causing the universe to accelerate its expansion. We might expect, as the universe expands, that gravity would slow down the expansion. But far from doing that, it looks like the universe is accelerating its expansion. And we give that label dark energy, even though we don't understand what it actually is. So this talk is called The Beginning of Everything, but I've tried to make it clear that by everything, I mean everything we can see. Everything we see of all the stars and all the gas and all the dust in our galaxy and all the other galaxies, the trillions of galaxies in the observable universe. And we're asking, where did all that come from? And I've been talking about the beginning of everything in that context. But everything in the sense of all the stars and all the galaxies, all the ordinary matter in the universe only makes up about 4% of everything that's out there. The other 96%, in other words, the dark matter and the dark energy, this 96% is still a bit of a mystery. But, as they say, that's another story. So thank you for listening to the beginning of everything in half an hour. Thank you all.